So this is EC 201, lecture 5. So for a quick recap of what happened at the end of last class, what did we realize? We realized that in general we are not going to encounter just a network with nonlinear one ports. A straightforward extension is to have a two port which is nonlinear. And when you have a two port which is nonlinear, if you think of the port voltages as independent variables and the port currents as the dependent variables, then I1 can be expressed as some function f of V1, V2, and in a similar fashion I2 can also be expressed as some other function g of V1 and V2. And f and g depend on what is inside the box, and in principle they can be arbitrary functions. If we now apply incremental voltages small v1 and small v2 in series with capital V1 and capital V2, then if we assume that small v1 and small v2 are within quotes small signal, then we can expect the port currents to change by a small value, and the new port currents are denoted by I1 plus small I1 and I2 plus small I2, where small I1 and small I2 are the incremental port current. Okay, and we can expand f and g as Taylor series, retain only the first two terms, and the last time around we saw that even though the absolute port voltage and the absolute port currents are related through a bunch of nonlinear equations, the incremental port voltage and the incremental port currents are still related by a set of linear equations. In other words, the incremental current I1 and the incremental current I2 can be written as dou f by dou V1, dou f by dou V2, dou g by dou V1, dou g by dou times the incremental voltages V1 and. During your study of linear networks in prior courses, you found equations which are similar in nature, where in a linear network you relate the port currents to port voltages, and the matrix that relates the port currents to the port voltages is called the admittance matrix or the Y matrix. This is also an admittance matrix. However, it is only valid for small signals or incremental signals. So it's quite logical to call this the incremental Y matrix. This incremental. What do we notice about the incremental Y matrix? What does it depend on? What all does the incremental Y matrix depend on? It depends on f and g and the operating point V1, and this is very similar to our experience with nonlinear one ports. In a nonlinear one port, the incremental resistance depends on the nature of the function f as well as the operating point, okay, which is the Vi of the. And once you have seen this, it is not difficult to imagine other sets of incremental parameters. You could have, for instance, of exciting the two port with voltage sources, you could excite both the ports with current sources, in which case the incremental current will become the independent variable and the incremental voltages across the ports are the dependent variable. And what parameter set will that correspond to? It will correspond to the incremental Z matrix. And similarly, if one port was excited with a voltage and the other port was excited with a current, then what incremental parameter sets will you obtain? What parameter sets relate? V2 I1 is some blah blah times I1 V2. The hybrid parameters relate. If V1 I2 is some matrix times I1 V2, that matrix is called the H matrix or the hybrid matrix. Why is it called the hybrid matrix? The dimensions of the entries of the matrix are no longer either ohms or Siemens, they are mixed. Okay, there are dimensionless quantities, there are ohms, there are Siemens. So all that I am trying to point out is that once you have seen this, the other sets of parameters are straightforward, just as straightforward a manner as. So this now allows us to do all that we did with linear two ports with nonlinear two ports, as long as the exciting signals are small signals. And just like in the one port case, we can define what small signal means in the two port case. How do you think we can extend the definition of small signal in the two port case now? So The only approximation in this whole process is that we have truncated the higher order terms in the Taylor series. So if we get rid of those terms, there is obviously an error made in the approximation. Okay. And we saw last time that, we all accept that as long as the error is say 1% of the approximate value, we still qualify that as a small signal. So by the same token, earlier we had, in the one port case, we had a one-dimensional Taylor series. Now we have a two-dimensional Taylor series, and the higher order terms, if they are all, say, if the sum of all those terms is say a small fraction of the first term, we assume that it is small signal operator. So the next thing is, as they say, a picture is worth 1,000 words. So it makes sense to understand, what these equations mean, drawing pictures. A multi-port network is simply a network with many ports, and so by definition a two-port is a multi-port. So the first thing is to look at the simplest case, which is the single port is the simplest thing to do. Let's take a linear one port. In our discussion on linear one ports, what did we assume? What is enough to characterize a linear one port? There is only one parameter required. It's very straightforward. This V is the voltage across the port, I is the current through the port. If I plot V versus I, it should be a straight line passing through the origin. If I say V was the independent variable and I was the dependent variable, the graph will look like. So further, if I constrain that the linear one port is passive, can I make any comment on the characteristic? What is a passive one port? What do you understand by passive? It does not generate power, okay? And we are talking about just resistive networks at this point. So in other words, if the resistor, if a one port for a passive one port, V times I must be greater than or equal to 0, which means that the IV characteristic or IV curve will lie in the first and third quadrants. Do you understand? If you have a nonlinear, you can again draw I versus V, okay, or V versus I, depending on which is independent and which is dependent, and you will get some arbitrary curve, okay. So let me just say, for example, a diode was something like this. If the nonlinear one port is passive, can you make any comment on the IV characteristics? A nonlinear one port, the IV curve will lie in the first and third quadrants. The element is passive. Is that understood? So the next thing is two ports. The first case is to consider a linear two port. And how do we characterize a linear two port? Let me take the Y parameter example. So I1 must be Y. I1 is Y11 V1 plus Y12 V2. Okay, and I2 is Y21 V1 plus Y22. So clearly the independent variables are V1 and V2. The dependent variable is I1 in the first equation and I2 in the second. So what kind of shape is this? I1 is Y11 V1 plus Y12 V2. It is a plane. So obviously it becomes impossible to depict it in two dimensions. One way around this difficulty is to plot. So one straightforward way of thinking about it is to plot I2 versus V2 for various values of V1. Does that make sense? This is just a way of representing a plane which is a three-dimensional thing on paper. You have seen this I'm sure you have seen this in several other applications before. There is nothing new, this is just background. So when V1 is 0, what is I2 versus V2? It will be a straight line to the origin with a slope Y22. This is for V1 being equal to 0. For V1 being equal to 1 volt, what will you get? The same thing shifted upwards. So this is for V1 equal to 1 volt. This intercept has to be y to 1, and the slope is still, similarly draw this stuff for different values of V1. Observation is that for equal increments in V1, what can you expect the spacing between these two parallel lines to be? So if, in other words, if I draw another characteristic with V1 being equal to 2 volts, the distance between the new line and the red line will be exactly as the same as the distance between red line and the black line. Okay, it's all obvious stuff. Okay, I just wish to point out all these things because we will do the same thing when you have a nonlinear device, and there things are a little different. And as jargon, these are called the output characteristics. And why does this make sense? What I am saying is that these set of curves where you draw I2 versus V2 for different values of V1 are called the output characteristics of the two port. And why do you think it makes sense to call them the output characteristics? Typically we are used to writing from left to right. Whenever you draw diagrams, the input is on the left and the output is on the right. That's why these are called output characteristics. Similarly, I could also plot I1 versus V1 for different values of V2, and these would be called the, if I plot I1 versus V1 for different values of V2, that would be called the input characteristic. Now, if you have a passive linear two-port, it is not straightforward to figure out anything about these characteristics. The only thing we can say is that if you have, what can we say? When you had a one port, you said V into I must be greater than or equal to 0. When you have a passive two port, what can you say? It doesn't generate power. Okay. So if it doesn't generate power, it can only dissipate power. V1 I1 plus V2 I2 must be greater than or equal to, that's all. When the passive two port is passive but non-linear, what happens? Can we make any comment about V1, I1, V2 and I2? When you have a passive two port, but not necessarily linear, the same relationship will hold even for a passive non-linear two port, because this is just a statement regarding energy generation within the net. Completes the preliminary stuff you need to know to be able to understand how we are going to go ahead and build amplifiers. We already discussed that it is not possible to have absolute power gain. An amplifier is nothing but as far as the source and load are concerned, it looks like a two-port network. Okay, so there is a source Vs, presumably with some internal resistance Rs. This is the load RL, and when we are trying to build an amplifier, what are we trying to do? If Vs was the input, you would like to produce as large a voltage as possible across, and also you would like to draw. Can you make any comment on the voltage across RL? Okay, should it change when Rs changes, or should it not change? Should that not depend on Rs? Ideally, we would like the output voltage to remain what it was, even if the source was of, within quotes, very poor quality. In other words, the output resistance of the sources is poor. Okay, and that also has the practical advantage that even when you replace the source, for example, this PA system has got an input port and an output port. You want to be able to use many kinds of microphones, and the gain or the volume setting shouldn't have to be changed every time you change the microphone, and different microphones are likely to have different output impedances. Okay, so ideally you would like to have an amplifier with one, a large gain, two, the gain should be independent of what? Rs. By the same token, these are all what we want. Okay, we can only go and design something once you know what you want, right? So it makes sense to first put down what all we want. Then we go and try and figure out how we are going to get what we want. The gain should be large, yes. The gain should be independent of RS. And why is that a practically good thing to have? The reason why you want a gain independent of RS is that this will enable the amplifier to be used with different kinds of sources, and the gain of the entire amplifier will not change if we change the source. Okay. By the same token, what about, can you just think a little bit? You would like to have a gain which also is independent of RL, isn't it? If you change the microphone, you don't want the gain to change. Similarly, if you change the speaker, you want the voltage gain to remain presumably the same. So ideally, we would like the gain to be independent of. Does this make sense? Okay. And this is the black box. We are trying to go and try and figure out what there is in the black box for these three conditions to be met. And of course, it might turn out that it is not possible to meet these three conditions all at the same time. Just like you want to study 2 minutes before the quiz, you want to get an S grade, okay? And this should be independent of the course you take, alright? So unfortunately, none of those three conditions can be met at the same time. Maybe in some courses you can, but okay. So just like that, you have a wish list, and maybe it is possible, maybe it's not. You have a 2-port, and a 2-port requires how many terminals? The simplest possible thing is to have a 3-terminal 2-port, and looks like, dealing with a 3-terminal 2-port is likely to be easier than dealing with a 4-terminal 2-port. So we will start assuming that the amplifier, we just don't know anything yet, so we'll say, okay, let's start with a 3-terminal 2-port where one terminal is common to both the input port as well as the output port. And in general, this 2-port network could be nonlinear. So it makes sense to say, okay, I don't know what the gain will be for large input signals, but at least let me first try and get a large gain for small signals. You always want to start simple and then see where things go. So in other words, I want, these three items in the wish list to be satisfied for, ideally for all signals, but at least for a start with small signals. Which means then that I have this 3-terminal 2-port excited by a small signal Vs having a load RL, and we need to figure out what there must be inside this 2-port in order that we try and tick off all the three items on our wish list. Does that make sense? Great. So since we have been talking about Y parameters, let us start with Y parameters. Okay, in other words, we'll try and figure out what the constraints on the Y parameters must be in order that all those three conditions are met. Okay, so you replace the 3-terminal 2-port with the Y network, and in general, how will the Y network look? If I express the Y parameters as a network, what will I get? Do you understand the question? No. How many of you don't understand the question? Okay. So if I write, let me call this voltage V1, this is I1, this is V2, this is I2. So I1 must be equal to Y11 V1 plus Y12 V2. Similarly, I2 must be equal to Y22. Alright. So can you think of a network which will implement these equations? Okay. So in other words, what would I do to replace the 2 port? How will I replace the 2 port with bunch of sources and impedances so that it implements these equations? Okay, so all I would like to do is replace. What should we do next? And we want gain to satisfy 2 or 3 conditions. So we're trying to find what constraints those 3 conditions impose on the y parameters of this box. Once you find the y parameters of this box, presumably we can go and find a way of building a box with these y parameters. Okay, which is why I have replaced the box with the equivalent y parameter circuit diagram. And so the next step must be to find, yes, so how will I find the constraints in the y parameter? First, the thing to do is to find the gain. Clearly the gain will be a function of the y parameters. What else? Rx and RL. Okay. Then we take a look at that expression and figure out what constraints they must be on the y parameter so that the gain is independent of Rs and RL, and gain must be as large as possible and all this other. So in other words, the next job is to figure out V2 by Vs. Since in terms of admittances, I might, instead of writing RL, I will say the conductance of the GL denotes the conductance of the load, and GS denotes the conductance of the source. And if you notice the input, things are mostly in shunt. So Y11 is in shunt with the current source. So it would seem that our calculations would get considerably simpler if you replace the voltage source in series with the resistance by the Norton equivalent. So let me do that. So what is the Norton equivalent of this guy now? Conductance of value GS, very good. And what else? A current source. So now can I make any further simplification? So what could I do? These two are in parallel. This is V2, Y22 plus GL. Okay. By the same token, Y11 plus. Okay. So we are now in business, and to make things a little nice and symmetric. So Kirchhoff's laws at node V1 results in Vs times Gs is the current flowing into the node, must be V1 times Y11 plus Gs, okay, plus Y12 times, and what is Kirchhoff's law at node 2 telling you? Y21 V1 plus V2 times Y22 plus GL equals 0. So they are interested in finding V2 by Vs. So we need to eliminate V1. So from the first equation, what do we get? V1 is Vs times Gs minus Y12 times V2 divided by Y11 plus Gs. Now plug this. So plug this into 2, and what do you get? Y21 into V1 plus Y22 plus GL into V2 must be equal to, okay, so now it's straightforward algebra. It's Vs times Y21 Gs by Y11 plus Gs must be equal to V2 times Y22 plus GL plus, okay, so Vs times Y21 times Gs divided by Y11 plus Gs is V2 times Y12 Y21 minus Y22 plus GL times Y11 plus GS by Y11 plus GS. Alright? I mean, this is all junk algebra. Okay? In a couple of minutes, we will get some intuition about why some of these terms make sense. Finally, we get what we want, which is V2 by Vs is Y21 Gs divided by Y12 Y21 minus Y22 plus GL times Y11 plus. Alright, so the first thing to notice is that the denominator is a, what form is the denominator? That's okay, it's a determinant, but you have term 1 minus term 2. So if there is term 1 minus term 2, what is a very real possibility? Okay. A very real possibility is that these two terms are positive and have the same sign, which means if Y12, Y21 somehow magically happens to be equal to Y22 plus GL times Y11 plus GS, then the gain becomes infinity. So gain becoming infinity means what? So you get an output even without an input. And have you seen that happening in this classroom a lot of times? You've seen it. Not you've seen it, you've heard it. Can you go and increase the volume there? Okay. This is output without input. In terms of Y parameters, can you now understand why this is happening? This is a 2-port. This is the input port, that is the output port. Is there, I mean, what, in a 2-port network, what is Y12 physically? What is the intuition behind, what does Y12 stand for? Y12 or H12 or Z12 or G12, they quantify, typically in an amplifier, if you yell if you whisper into the input, it must sound like somebody yelling from the output. Okay? So in other words, you want only the output port to be influenced by the input port. Okay? What is this Y12 parameter? It quantifies the effect of the output port on the input port. You understand? Y21 quantifies the effect of the input port on the output port, and Y12 quantifies the effect of the output port on the input port. Okay? So in this room, for example, what do you think is, where is this Y12 coming from? This is the input port, that is the output port. Why is the output port is there any influence of the output on the input again? Yes, why? So the sound goes, hits the wall at the back and comes back. So there is definitely a path from the output to the input. So if I model this as an acoustic 2-port, there's a lot of Y21 because of the amplifier there. But there is also Y12 because of this path, okay, goes there, hits the wall and then reflects back. Okay? And if I make Y21, finally it is not possible to make Y12 0. Okay? In practice. But, so, which means that however small Y12 is, you can always make the gain infinite by, see, if Y12 is very small, you can always make the gain infinite by increasing Y21. That's what you just saw now. Okay, by increasing the volume, the gain of the amplifier, you are increasing Y21. Okay, and you can always increase it such that you will eventually get a gain of infinity, which basically means that the system is unstable. But all I wanted to give you is to give you physical intuition about what happens when there is Y1. You understand? So clearly, if these two terms become positive, both these terms are positive and equal, then there is a very real chance of the amplifier oscillating. Okay? Now we saw an example here in the acoustic domain. So what is, as an engineer, what is the easiest way of eliminating this possibility altogether? Okay, one way of doing it is to say either the problem term is Y21, Y12. Okay? So one simple way of eliminating this possibility altogether is to simply avoid this difference of two terms in the denominator. If you want to avoid the difference of two terms, you just make one term 0. Okay? So one thing seems to be, there's hardly, you can't make the second term 0. Y22 plus GL times Y11 plus GS cannot be made 0 because GL is positive, GS is positive. So the easiest thing seems to be to make Y12 times Y21 0, and if you want to make Y21 times Y12 0, there are three ways of doing it. What are the three ways? You make Y12 0, you make Y21 0, or you make both of them 0. Okay? If you make Y21 0, what happens? Everything is 0. Numerator is also 0, so you have no gain. Okay? So that doesn't make sense. So that leaves out two possibilities are gone. That only leaves out one possibility, which is Y12 must be 0. So to avoid this, so this is the first constraint on the Y matrix. Is that clear? Okay. So now, if you now eliminate Y12, if you set Y12 is 0, what happens to the expression? We remove this term is not there anymore. Okay. Alright. So now you want a gain which is independent of GS. So the next thing is independent of, how does GS appear? Gain is basically Y21 times minus Y21 by Y22 plus GL times GS by Y11 plus GS. So if you want to make this independent of GS, what must you do? Set Y11 to be equal to 0 to make gain. Alright. It comes out of the math, but is there a physical way of looking at it and understanding why this makes sense? Let's go back to this example here. Okay. Let me copy and paste, and we said Y12 was 0, so we eliminate this guy. Alright? So if you want the gain from the input to output to be independent of GS, how will that happen? See, the only reason why the gain, the output voltage V2 would depend on GS is when current flows through GS. Correct? If there is a current flowing through GS, there is a drop across GS, so V1 will change, which will in turn cause V2 to change. So eliminating dependence on GS is equivalent to trying to and reducing current to 0. In other words, Y11 must become, the input impedance looking in must become infinite so that the current is 0, which is equivalent to making the input conductance become 0. Does that make sense? So very good. So what is the gain now after we've eliminated? Okay, so we've eliminated dependence on GS, which is now we want gain as large as possible, which means what? Denominator should be as small as possible and numerator must be as large as possible. So what can you do with the denominator? So numerator must be large, which means, pardon? Come on people, what is there in the numerator and why is there? Y21 must be as large as you can make it. And the denominator must be as small as possible. Which implies we have hardly any control over GL, right? Because that's the load. So how can you make the denominator as small as possible? You make Y22 0. So which means now that massive expression for gain has become V2 by Vs is minus Y21 by GL. And clearly the gain, does it depend on GL or does it not depend on GL? Depends on GL. So you live with it. So if you have to realize the other three constraints, looks like you can't get the gain to be independent of the load. So in other words, if you want to make an amplifier, you need to have a two-port network, whose incremental parameters are the following. So we need a box with can you help me fill out the entries in the matrix? Y11 should be 0. Very good. Y12 0. Y22 0 and Y12 as large as possible. Then when you hook it up, you will be able to get incremental gain, where the value of the incremental gain will be independent of the source resistance, will not have any strange condition where there is an output without an input, and for a given GL it will have as larger gain as possible. So I think this is a good break point, and tomorrow we'll see how, what a nonlinear device with such an incremental matrix, how will the